Okay, want to continue on from last time. We talked about the OSI model, which is a 7-layer model, and gone more out of fashion nowadays. TCP/IP has kind of taken over everything, and so it kind of has a 4-layer model that incorporates what was in the 7-layer model. And here is a nice picture showing the different layers of the OSI model versus the TCP/IP, and mainly you'd be concerned with the TCP/IP layer hierarchy. And looking at the different layers, the link layer, it says it includes device driver and network interface card, and it combines on the OSI model our physical layer and then our link layer, which is dealing with things at the frame kind of level. So the physical layer says, okay, are you putting voltages out on a wire? Are you putting light on fiber? How are you actually putting the ones and zeros on, and isn't concerned about what the bits represent? And the link layer then takes the bits and it puts them into frames of data, and that's where you have the MAC address, media access control access. Sometimes you'll hear it as a NIC or a network interface card access. So that is that 6-byte flat file addressing scheme that usually it's in a E² on your network card or so on. And so just like we have at some of the higher levels on the link layer, you know, there's the 6 bytes, the first 3 bytes is known as the organization unit identifier, and that's the manufacturer. And then the last 3 bytes are the individual card. We also, if you see, for instance, all ones as the address, so you have 6 bytes, FFFFFF, and so that is a broadcast. So just like we have on the IP layer, a broadcast, we have on the at the frame level and so at the link layer. And so things that, for instance, if at that network link layer in the LAN, you would broadcast out to say, for instance, hey, who has IP, you know, 10.0.0.5? And I would broadcast that out to everybody, and somebody would reply with an ARP reply and say, that's me, here's my MAC, and then I cache it in an ARP cache so I don't have to broadcast for every frame, and then I will forget that cache disappears, you know, from 5 to 15 minutes kind of thing. And it's to reduce the broadcasts on the network, because if I'm sending 1 frame to you, chances are I'm sending a number of frames to you. And so that's, if you see this ARP and reverse ARP. And so link layer, and then we have the network layer, which is kind of straight across over on that. And so we have IP, and so there's different protocols that you'll look at there. And then with an address on the IP version 4, which typically you've used, although IPv6 is around, but IPv4 has 4 bytes of information. And so that is enough information, again, to get a packet anywhere in the world. And so what we do is we still have our addressing and stuff at our link layer, but then we put the addressing on the network layer, and that gets us to an end node anywhere. And we say node, it could be a router, it could be a computer, a destination for the network. And then from there, we have the transport layer, and it says it provides a reliable flow of data between 2 hosts. So a network layer was able to get me to the end node, the end machine. But then I need another address to say, get me to the application on the end machine, and that's our port numbers, okay? And then our application layer, which again takes up what was 5, 6, and 7 in some of the OSI model. And those are the different protocols that will run on either TCP or UDP, depending on the protocol, which runs on IP, which runs on our Ethernet frames. And so things there, HTTP, so our web services, our mail, our file transfer protocols, and that kind of thing. Now, the way to look at this is it's known as packet encapsulation. So here I'm talking about all the different layers, and how the layers react with each other is, again, we have physical layer, and then which is the bits, and then we put the bits into these frames, and then we put them into packets, and so on up the way. And so data is sent down the protocol stack. Each layer adds to the data by prepending different headers on top. And so if we look here, you have some data that you wanted to send. And so if I have my data, and it could be just your name, for instance, and a temperature or something like that. When we look at the physical network, we're just ones and zeros. And again, is it maybe a voltage? Is it a light, no light, something like that? When we get up to the data link layer, we said, okay, we have a frame. Well, so we bundle the bytes, the ones and zeros, which it doesn't know anything about at the physical layer. It's just whether I turn something on or off, or that kind of thing. But we bundle it up in the data link layer also to frames. So if I had my data here, and this could all consist, it shows IP, TCP, it shows all of this kind of stuff. So we started off way up here at the application layer with some data. I have my name, colon, space, and a temperature. Well, how do I deal with that? Well, I send it to the transport layer, which says, hey, it's going to a machine somewhere else that is sitting, maybe it's a web service, so it's sitting at maybe port 80. So I would have in the TCP or UDP header, there's some information, including that socket address, that port address. And so with that, I say, hey, I want it to go to a web page, and it's from a certain service. So I sent information. I'm sending information from this layer to here, and I choose a random port number above 1024. And we see that when we look at our packet sender. Our addresses are some wild number above 1024, and we're always sending it to, I don't know, we said 7777 or something like that. Okay, and so that goes header with that information is stuck on the data. And then the transport layer sends it down to the network layer. And the reason we have all of these different layers is you can pull out a layer and replace it with another set of protocols at that layer, the transport layer. For instance, all of stuff below transport, I could send something via TCP, which has that kind of handshaking acknowledgement thing I said, or I could send it via UDP, which says send it and forget it. So it's a lot lighter protocol, and I can leave all the layers, network layer, data link layer, physical layer. I can just replace that one layer, and none of the rest of the stack knows it. None of the rest of that protocol stack knows it. And so really the transport layer here is talking to the transport layer. You can think of this data coming down this protocol stack, going across whatever medium and going back up the other side, up this thing. As far as the transport layer is concerned, it's talking to a transport layer on the other side. It doesn't really know how that's all happening. When I send the data from the transport layer to the network layer, I go and say, okay, well, this was the application. So the transport layer says, I'm sending to port 80 and I'm from 7777. Sends it down to the network layer, and the network layer takes that and goes, well, I have to get it to a machine, and it's at 10 dot whatever, who knows where. And so, and I need to say where I'm coming from. So I say, it's going to this address, it's coming from this address, and then I bundle up as part of the data, as far as it's concerned, the TCP, UDP, and the data. That's all going. And so I'm sending it to the network layer on the other side. And so it goes up the protocol stack on the other side, and the network layer talks to the network layer on the other side. And so that has my IP header, which again has source and destination, all that. I said one of the other things it has is time to live. Very clever thing. So if I sent it to somewhere that doesn't exist or is no longer online, it doesn't have your packet traveling the world, just going from router to router, going, do you know where this thing is? Every time it goes through a router, it decreases a number off the time to live. Eventually, that gets to a number below which a router goes, I'm going to throw it out. Could be 0, could be your router could say, if I see a number less than 20, it's from some garbage place or whatever. It's hopped too many times around the world, throw it out. Don't pass it on. And then the network layer, so we have our IP, that gets us anywhere in the world. And then I have the data link layer. And so the network layer bundles this all up, passes it down to the data link layer. And in the data link layer, I'm talking about data to be able to get out of this network or just get to this network. From the data link layer, I can't get out of the network. But on the IP layer, if I was said I want to send it to a machine that's in Australia, then when I pass the information down to the data link layer, where does it send it? It needs to know where the router is, the gateway is, because it has to get it out of this network. And it can't get it out of the network. It's at that layer, you're in the network. You can't get out. And so it wraps up the addressing and stuff to someplace in Australia, for instance. Here, all of that's part of the data. And in the frame header, we have the address of the router. And then when the router receives this, it goes up the protocol stack, it sees this, and then it says, okay, it goes up to the IP layer, and it goes, oh, well, that's not in my network, so then routers are going to talk to other routers. One router is going to respond and say, hey, I'll forward that on, and then it goes down the protocol stack, and the frame header gets the MAC address of the whatever router said that it could deal with it, and it sends it off to that. And then that router takes it and figures out where to send it to, and it gets a MAC address for that one. And so this constantly is changing. The destination and source never change from going from source to destination. And so typically you go through hops on your network. You're going up to the network layer, checking things out, going back down, up to the network, when you finally get to the destination, then it goes all the way up on your application. Okay, each layer talks to the equivalent layer on the other side. Now, being that we're sending stuff out over the wire, we also have our frame trailer here, which has a bunch of checksum. And typically, even at the network card layer, if your frame is malformed, it'll toss it out and it won't pull it up the stack. Okay, and there are modes. You can put network cards in promiscuous mode and things to say, hey, just show me whatever's on the wire, even the garbage, because I've got to figure something out. But typically, it will just toss it out if it's not working, or if it's not properly formed and with your checksums and all. If we look here, we see that we have from the, not including the frame header and a frame trailer, we have 64 to 1500 bytes over there for our data. And that comes from way back when we were hooked up onto a coaxial line, and we had one coax to one machine to another machine to another machine. And then they said, okay, I said that the protocol for Ethernet was what's known as CSMA-CD, Carrier Sense Multiple Access with Collision Detection. So we say carrier sense. So there's a node way over there on the other side, and there's me, I'm a node over here, and I want to transmit, and the first thing I do is I listen. That's the carrier sense part. Multiple access means all of you can transmit on the same line, and then collision detection. So when I listen and no one's talking, then I'll send something on the line. So I'll start talking. And when I start talking, I listen to what I'm saying. And if what I'm hearing is not what I'm saying, somebody else is talking too. And so then we do collision notification, and we do this jamming sequence on the line to let everybody know that there was a collision. Then I do a random back off. and then listen on the line to see if anybody's talking. And because it's a random back off, the thing I collided with, it did that jamming sequence and random back off too. And then one of us will listen first. There will be no one talking, hopefully. And then I'll start talking and listening. And then the other thing that collided maybe with me will listen, and they'll hear me talking, and then you won't have that collision. So that's how CSMA-CD in short kind of works. Now, the more collisions there are, the more retransmissions there are, the more that your throughput drops on the line. And hubs, for instance, as more and more traffic got on the line, their performance would degrade. They came up with switches to say this net part of the network might be talking, and as long as you're all talking, one talks to the other, I could have two nodes talk over here, and the switch can make those connections, and the throughput goes up. Okay. Yeah.
Where does the sizing come from? Like, how is IP and TCP both 20 bytes if they're different sizes?
Oh, so the header has a whole bunch of stuff, and we'll look at some of the headers. So there's source and destination address in there, but there's the time to live, there's sequence numbers, there's all sorts of things, and we will look at a header coming up. But there's more information than just the source and destination. Otherwise, yeah, a good answer. But the 64 to 1500 bytes, where that came from, was what is the minimum I can talk? So I'm over here and I'm talking. How long we have networks, you can hook up to 5 connections on a hub, 3 need, so the maximum distance of your network and the minimum amount of bytes, I need to be still transmitting when it gets to the other end. Because if I transmit and get off the line before the end of the network heard the communications, there might be a collision and I might not know about it. So there's a minimum number of bytes to get on the wire to ensure that when I transmit, that the node at the farthest end would hear that transmission and know that there's a collision. Otherwise, we could lose some of the data. So we have 64 to 1500 bytes on our frame. So when we look at IP, so we look at kind of this kind of region. So we have this frame, which we said was the MAC address, and we have, because we're actually putting data out on the wire, we have this checksum frame trailer. When we go up to the IP level here, we're responsible again for end-to-end transmission. We send data in individual packets. The maximum size of the packet is determined by the networks. If we have more information, we can fragment it out into multiple packets, and there is a sequence number in the header, for instance. Unreliable just at IP. Packets might be lost, corrupted, duplicated, delivered out of order. And that's the thing. The cool thing about this all came from the internet, came out of kind of the military and DARPANet. They were concerned that, for instance, in a war situation, that their transmission lines, communication lines could get disrupted. And if you need to send some information, and you had lines going through Seattle and somebody nuked Seattle, how do your information still get there? So if you put things into packets and then routers talk to other routers and you send information, it is always looking for the best way forward. And you could send, go look at a web page in Australia, and it might send some things off going to the east coast of Canada, and it might send some stuff down California way. And in your same getting information, packets don't have to go the same way. And it could be there's a surge in demand in one place and the network slows down, and so a router goes, well, this is better, so it'll send packets. So some packets that you sent could get there before the first packets you sent. And so there's sequence numbers in the headers and things, so it can put it all back together. And so the idea being that if something somebody accidentally unplugged the router or it crashed or whatever in the middle of you sending, it goes, that's no longer a path, and it sends your data somewhere else, and communications keeps going, hopefully. Although you see where, whole swaths of, servers aren't available sometimes when something happened with some of the routers and things. Okay, IP addresses. So we are 4 bytes. An example is 163.1.125.98. So 4 bytes. Again, there's IPv6, which we have 6 bytes of information. Each device normally gets one or more addresses. In theory, there are about 4 billion. And there was a big concern because we've run out of, there's far more devices than there are for our 4 billion addresses. But a lot of times, for instance, you have non-routable addresses. So the 10 dot whatever network is normally a non-routable. So I use it in here. The different schools will use it. Even different networks will have the 10.0 network. And we use that typically because I'm not expecting the data in a 10 network to get out of the college because it's in a 10. 192.168.x.x is another one. And so there, you'll normally see routers and stuff at your home, and it could give all your different devices a 192.168, or it might give it a 10 dot something, and it's just for use in use. Everybody else that has like a Linksys router or whatever, they're all using that same. Now, facing the world, you're getting just an address, one IP address from Shaw or TELUS or Rogers or one of those. And so there's what's called a network address translation. So it'll take your local addresses and keep track of who's wanting stuff, which device in your home network is wanting stuff versus the world. And as far as the world sees, or as far as Shaw or TELUS sees, you have one IP address. And so that's the way we have far more devices than we have addresses. Now you can set up IPv6, and again, I think they say there's more addresses than there are grains of sand, but you can set up IPv6 and directly address your individual items and things. And typically there is a few IPv6 routers around that will directly talk, like I say, to your individual devices anywhere in the world. We might talk about that coming up a little bit more. So, routing. How does a device know where to send a packet? All devices need to know what IP addresses are directly attached to their network. If the destination is on a local network, send it directly there. And we said MAC address. Now the network mask is what determines that. So for instance, in a class C, we have 255.255.255.0, and we had talked about that. So when you look at your network mask, the reason this is working, that's a class C, we're saying, okay, anywhere where there's ones, if I had my network, let's say it was 10.0.4.5, if I have that, this is typically called a class C, a class B, a class A, okay, in the old classing system, because you can carve it up. If I have a class C, I can go from 0 to 255 here, right? So 0 and 255. The 0 is reserved because that's the name of my network. So my network in this case is 10.0.4.0. That's the name of that network, okay? And so my router just has to keep that address for my network in its RAM. And so when packets come in, they say, hey, is it for 10.0.4.0? Now I'm picked a non-routable one, so that's not, but if it's for one of the networks that can be seen in the world, so it's saying, hey, do you have 10.0.4.0.5? Well, all it needs to know is that this is one of their networks. And if so, take the packet in and then do an ARP and say, hey, do a broadcast out and say, who's got 10.0.4.5? and some machine, if it's there, will reply with a ARP reply, that's me, here's my MAC, and then I send it via that frame layer to out. Okay, so the dot zero is the network. The dot 255 is the broadcast. And so if I send out all ones in your network, everybody listens because I'll broadcast out to everybody going, who's got, and then somebody will reply. Okay, so we have the broadcast and we have the network name. So there's always whatever the class is minus two. One's the network, one's the broadcast. In kind of more, this is also known, this class C is also known as a /24 because there's 888. So we've got 24. I could have a dot 23 and take one of the bits from this and then give this, instead of having a 0 to 255, have my 0 to 512, so minus 2 for the number of hosts. So you could have a /23 or a /22 or a slash, and that's how you would figure out. So instead of this, we would have to make it so it's all ones with a 0, right? So uh, so if I know that the destination is on the local network, if looking at the network mask, this shows that you're on the network. If you are not on the network, that means I have to send it somewhere else, which means I have to send it to the default gateway. Again, look in Windows, you see the default gateway, which is typically your router. So if I am asking for information and it's to an IP address that is not in this network, it goes to the router, and then the router has to talk to other routers with all sorts of different protocols and figure out where to send the information. If the destination, again, isn't local, most non-router devices just send everything to a single local router. Routers need to know which network corresponds to each possible address. Allocation of addresses is controlled by this ICANN group, which has a fairly strict set of rules on further delegation to avoid wastage. You have to demonstrate actual need for them. I think basically all the addresses have been used up. Everybody's got them. But typically, if you're getting connecting up to an internet service provider, they will provide you with one. Oftentimes, unless you pay more money, your IP address, like at Shaw or TELUS or Rogers, it's dynamic. Chances are it's the same for a long time, but it doesn't have to be. For instance, you turn off your computer, you bring your laptop somewhere, you go back home or whatever, or if your router goes off or power out and comes back on and things, you have a lease time for the address, and then it will ask the DHCP server for another address. They typically will give you the same one back, but maybe your router was powered off at the time some of the leases expired, somebody else grabbed your address, and you could start off with another address. Okay, so you don't have a static address. You pay more money to guarantee you always have the same address. They'll all say, yep, I for sure will have that. And then you could set up home servers and things like that, and from anywhere in the world go into it. Now, you can always have a device on your network whenever your address changes, notify you about what the new address is. And there are some different websites that, in fact, some of the routers even have it so that you can put in these dynamic addresses. And so every time your address changes, it notifies this remote server, and you get a name, for instance, Mel's home.com, if that was there or whatever, and it will reassociate the new IP address every time it changes. So, and there's paid services for that. There's some free ones and things, so you can do all of that kind of stuff. Okay, as far as IP packets, so again, we're at that layer. We have source and destination addresses. And so as part of that packet header, we have the source and destination. And then we also put in information, for instance, which type of protocol is in there. Because in IP, we have TCP and UDP, and then ICMP, which is, I can't remember the messaging protocol, and then various different options to control fragmentation. Again, there's places to put sequences of fragment numbers. So if you're not just sending a single packet and your information is broken up onto, how do I put them back together? Because some packets could show up that I transmitted later could show up first because they went a different route. And again, this time to live. So I'm sending it, for instance, out to somebody and they aren't there anymore. They've packed up. I send it to a laptop in 204, but that person graduated a year ago. They'll never be back onto there. So how do I make that kind of go away? And so time to live was an important part of that. So let's have a look just at IP, for instance. And so this is just talking about this header. Let me go back here. And come on. Okay, so this is this here. Okay, and so at that layer, what's in that header? So we have there's the version, for instance, is it IP version 4, IP version 6? How many, the length of the IP header in bytes. And so how many bytes long is this whole header? And so then the type of different service, the total length of the entire datagram, so not just the header, but the whole thing. Then there's IP addressing identification. So that's if we're going to have different fragments of it, whether you're allowed to do more fragments or not. And then there's another number for fragment offset, time to live, maximum number of routers it can hop through, although some routers can take more than one off the number. It's not like saying 20, I'll go through 20 routers and then die. There can be all sorts of different numbers, and your router will take something off the time to live every time it goes through it. And then we have our protocol. For instance, if it's 6 in here, you're sending TCP. If it's 1, Internet Control Messaging Protocol is there. 17, we're sending UDP. And then there's the checksum for the header, so making sure all of this data is right. And then we have the source address and then destination address. So I'm sending out, for instance, I'm saying who it's coming from and then where it's going to. And then when at the network layer, at the IP layer on the other side, I know how to send back to you because you sent me your return address. And so if I'm going to send back to you, I could copy that IP datagram and switch the source and destination addresses, and I'm sending data back to you. Okay, and then we have different options. There could be timestamps, all sorts of things, and then there's padding to make sure that it pulls out to these 32 bytes along for the header. So each one, we've got 1, 2, 3, 4, 5, 6 here going of 32 bytes in our header, and then the data. And the data is in the IP end of things is going to make up your TCP header and the data, okay? And so that's all going to be in there. We, so far, have only looked at just really the protocol number IP addresses. And again, how then we route this, and we talked a little bit about it. So we have my machine here, and let's say I'm asking for that packet sender to display on TCP, for instance, the data and show it up on the little screen of that packet sender application. So on this side, I've got an application that is going to send TCP, and it's going to be your AT firmware in your node MCU, and it packages information to transport, and in there, in the actual AT commands, we say whether we're going to send TCP or UDP, and then that packages it up to the network layer with the data, so your name and your the temperature, for instance, and then it says the network layer. So in there we have what IP address we're going to send, and it's going to take the socket number you're going to send to from the transport layer, and then it goes out the link. In this case, we are using our 2.4 gigahertz Wi-Fi, and then it goes to the router, for instance, if it's going out somewhere else in the world, or if it's going locally, then it will connect up. And so we could go from the link layer and have the MAC address of the router go up to the network layer, and it could say, oh, this is in Australia, so we need to then send it off to another router, which will get the MAC address of whatever the other router is, whatever communications medium it goes, and it will send it off. Now, this other router, maybe that goes through multiple routers till it gets to Australia, and then it goes up and it says, oh yeah, that's in my network. And then it goes and says, okay, does an ARP and says, who in the network has this IP address? Somebody will reply back, and then it will send it over to the destination node, and then it goes up to the network layer, it goes up to the transport layer, and then the application is talking to the application. So any one of these can be pulled out and replaced with another thing. So again, on our transport layer, I could just say, I want everything else to be the same, but instead of going TCP, we're going UDP, for instance. Okay, and so that's kind of how it goes through from one router to another router. It's going to mainly take your whole bundled data and go from the link layer to the network layer, link layer to network layer, hopping around from router to router to router till it gets to destination machine. It'll go all the way up there and decode your application. Okay. UDP is a thin layer on top of IP, and the lab that was this week is about getting your AT commands to work in a just using your ARM board to be able to send some TCP. I said that you'll have some time, so yeah, we have a test this week, and it may take some of the time. Next week, we're just going to change TCP to UDP. Basically, everything else stays the same, and send it still to the packet sender, but then we're going to look at the UDP packet on the wire. So this week's lab, I want you to get your logic analyzer out and look at the bytes that are transmitting on the serial lines. And then next week, we're just going to change TCP to UDP. And the reason for it is UDP is much more lightweight. With TCP, we could still look at it, but there's a whole bunch of handshaking going on. Send me packet 1. Acknowledge that you sent me packet 1. Send me packet 2. Did I get packet 2? Acknowledge. And there's this sliding window and handshaking going back and forth. With UDP, I say send it, and that's it. Okay, so I look at this little packet, that's it. Okay, so it just simplifies things for looking at it. So I just was saying, okay, we have a thin layer on top of IP. If you use TCP, because of the complexity of it, my application has to worry less about getting the data. I'm going to get the data, chances are, if I'm sending stuff with UDP. So my application doesn't have to worry about it as much. It's not like if there may be a network down and you don't get anything, but if I'm getting data, it's corrected, things are in the right order. With UDP, I send it and forget it. So if it matters about you getting information on UDP, UDP doesn't care, so you have to care. Your application would have to do that. Okay, so that's kind of the differences. So there's less overhead in UDP, but if it matters, your application has to deal with it. In TCP, the network protocol stack took care of making sure that transmission happened. So this is a thin layer on top of IP. We add basically our packet length and a checksum to guard against corrupted packets. There's a source and destination ports. Ports are used to associate a packet with a specific application at the end. Again, you know, on UDP, where am I going, for instance? Still unreliable, duplication, loss, out of orderness is possible. But here's the UDP header that's on. So we have a source port and a destination port, the length, and then just a checksum saying that we're not corrupted. So every, like the data link layer, we have checksums on here, and then your application data. And so we're going to send that on the wire. We'll have a look at how, because UDP is on IP, which is on the Ethernet on the frame layer. So we have that to decode. Fortunately, there's programs that will let us see that on the wire. And we're going to look at one called Wireshark. And so we'll download Wireshark and have a look at it. One of the things to mention about Wireshark is it is a network sniffer. And so if you were looking at some of this and you were working somewhere, you have to make sure that the powers that be in your company know that you have this, and that you're not trying to spy on anything. People have gotten in a lot of trouble, especially some military people that were just using this kind of thing and for coursework, but you know, the people in powers that be weren't aware of that or didn't authorize that. So in your home network, you're all good. But just if you're doing anything at work, make sure that somebody knows that you're doing it. But I can look online. And it used to be that, for instance, a lot of, we're going to use next term SSH, Secure Socket Handler, to communicate to our Linux boxes and things. Telnet was the big thing for many, many years, but Telnet sent everything unencrypted, names, passwords, all the rest. So I could just sit with something like Wireshark. It used to be called Ethereal, and then there was some sort of trademark dispute, and the people that did the open source Ethereal changed the name to Wireshark, and now that's kind of what you'll find. And we'll fire it up. We'll have a look at kind of the things it can do coming up. But so we have our UDP, and we're going to look at a packet, and we're going to look at the different segments of it when we get over towards there. Typical applications of UDP where packet loss is better handled by the application. There's sometimes, for instance, it says voice over IP, network file systems, most games. It's not like network file systems, for instance, or games. You go, it's not that you don't want or don't care if there's any errors. You do, but your application might be able to perform things in a more real-time fashion than the typical TCP/IP handshaking. So it leaves it to the application. So UDP just fires it out and goes, I don't know if it got there, I don't care. And then your application, if it cares, has to deal with that kind of thing. And so some things like streaming and stuff where I can't afford, if something dropped, I can't afford maybe to ask for a retransmission. And depending on how things are set, maybe I can rebuild missing packets or missing bits of information in a packet or that kind of thing. Where overhead of a setting and connection isn't wanted for doing a full TCP IP connection. TCP is reliable, full duplex connection-oriented stream delivery. Interface presented to the application doesn't require data in individual packets. Data is guaranteed to arrive and in the correct order without duplication. So before, again, there's this acknowledgement and negative acknowledgement happening in TCP. So the end, the TCP at the end, that goes, I've got this packet, I'm waiting for the next one, and so there's this handshaking going back and forth. So data is guaranteed to arrive. I wait to say I'm still waiting for packet 5240, and until I get it, and in fact, if I don't get it, I'll ask for a retransmission, and you'll get that kind of thing. So because that's all in that TCP, my application doesn't have to be as worried about that kind of thing. You're going to get the data, it's going to be in the correct order. You're not going to get multiple versions of packets. Sometimes you get that too, but you could get data being sent, and because of whatever reason on a router, it didn't think it sent, it might send another packet out. Significant overhead applications of TCP, file transfer protocol, hypertext, so the web services and things like that. MQTT got sent over that as well. I'll talk about MQTT coming up. That's machine-to-machine communications. And despite that, there is MQTT over UDP, but most of it's under TCP. And it's kind of a lot lighter weight than if you're doing stuff through web servers and things like that. Saves the application a lot of work, so it's used unless there's a good reason not to. Again, if we're just sending temperatures and I'm sending them every 5 minutes, and if we miss an hour's worth, it really doesn't matter, kind of thing. Then I just could send UDP. It's a short blip. One of the things I like about UDP, for instance, is if I have a battery powered device, I can wake up. I can be running on a coin cell. I can wake up, blast out sensor data, and then go back to sleep, and then try and get as many months as I can on a coin cell. So wake up, send, and the quicker I can send stuff and go back to sleep, the longer my battery life. And so that's where you'd use something like that. TCP implementation, again, that we have connections that are established for this, known as a three-way handshake. Data is divided up into packets by the operating system. They're numbered and received and acknowledged. Connections are explicitly closed. And we have source and destination ports, this sequence number to order the different packets, and acknowledgement numbers used to verify which packets are received. And so we have a TCP segment, so it's a little bit more, we've got a little bit more stuff than just our UDP that's going in there. So we have, again, source and destination port, our sequence number, our acknowledgement for the next expected sequence number of the next expected octet, and then length of the TCP header, the number of octets, and so you just need to know port numbers, sequence, acknowledgements. I won't be delving into really the TCP. We're going to look at UDP going because it's nice and straightforward on this. But TCP data transfer, so I have a client and we send packet 1. So there's a timer. So if the packet got lost, it should arrive, an acknowledgement should be sent, but an acknowledge wasn't sent. So if I'm saying, hey, an acknowledgement should have been sent by this time, but it wasn't, then I retransmit packet 1, and then when the receiving device receives it, then it sends an acknowledge, and before the timer goes off, then I receive that acknowledgement, and then I can send packet 2. So that's a lot more communications, handshaking work than it is to just say, I'm just sending you a packet and forgetting it. And on a battery powered device, I don't want to wait for all of this and wait to see the packet in this. I just want to send you something, chances are, and then just forget it. Okay. We'll stop there. We'll continue talking next time. I see some of you in the test this afternoon. Again, there's also a lab. You have time this week. You have time some next week. You are going to change one line, TCP to UDP, and we're going to have a look at something on the wire next week as well. But we'll talk more about it as we go along.